Definite integrals, they're all about area, aren't they, right? Well, they tend to be, or about accumulated changes. The thing about them is when they've got boundaries, right? There are some different rules or some special rules that apply to them and don't apply to indefinite integrals. I'll give you an example. You know that if you integrate a function, right, and we usually think, you go from A to B, right, and we tend to think of these lower and upper bounds as being smaller and bigger. I guess that's why we call them lower and upper, right? You go from 0 to 1, or pi on 2 to pi. That's the kind of idea that makes sense, right? So you think, if you integrate something, that's what gives you the area, okay? However, we also know that you can switch them around, can't you? There's nothing stopping you mathematically from just doing it the other way around, okay? What effect does that have when you evaluate it? What effect does it have? You could give it a go, couldn't you? You could actually evaluate it. If we thought that if we called that f and so its integral would be f prime, okay, you end up with something like this, and then you have to evaluate it at b and a, but you swap the order, right? So this is going to be f of a minus f of b, isn't it? The other way around. And so this here is backwards to what we're used to. It's backwards, right? But therefore I can go back and see, well, I can express this as the definite integral that I started with. It's just that there's a minus sign out the front, and the order is what you'd normally expect. Right? So you have little things like that. Other things like the fact that, from this step to this step, right? Can you see, it didn't matter that I had an x here. It didn't matter what the variable was. I could have called this t, and I would still have stuck a and b in, and the t would have vanished, right? And so that's why we give the variable. It's not just called the variable integration. It has another name. You guys met it before when you first did integration? What's it called? It starts with a D. It's a dummy variable. That's right. These guys, if it's a definite integral, right? They're just there as kind of a they're just keeping the seat warm, really, okay? When you're doing your calculation, they're gonna go. You're gonna get rid of them. They're just there just as a placeholder. So you can put something there and say, that's what I'm going to put numbers into, okay? So therefore, I could just as easily say, for instance, an integral like this, I'll write a normal one. If it's with respect to x, it could just as easily be with respect to, say, I don't know, theta, or with respect to t, or with respect to any variable you like, because the variable is going to go in the end, okay? So these kinds of things, these are the two main examples of things that only apply to definite integrals. Obviously, it doesn't make sense to say any of these things about indefinite integrals, because it's all about the boundaries, right, and how they interplay with the whole integration process, okay? So you can use things like this. Actually, that's just 2-unit, right? But you can use it to get other results. I'll give you an example. We'll look at it visually, and then we'll prove it algebraically, okay? Here we go. Prove. The danger with so much in extension 2 in general, right, is that it's all just letters, except for that 0, right? And so it's like, what am I even doing? Be careful, right? Let's think of an example and see how this plays out, okay? Let's think of something nice and easy to integrate. Something like, say, I don't know, e to the x. Let's do e to the x. This is an example of this, okay? Because once you put in an actual function, we can draw it and we can see it, right? So if I imagine that that's what I'm considering as f, right? Then I'm going to consider this, e to the x, e to the minus x, dx. Okay, now, here's my example. Draw this with me. What does this look like, okay? This is an area. This is an area, and it's symmetrical about the y-axis, isn't it, right? So, well, the boundaries are symmetrical, I mean. So if I put minus a over here, for instance, right? A is going to be the same distance on this side. So there you go. I'm working out an area like that, right? Now this statement apparently is saying this is equal to two other areas. These two areas can, by their powers combined, turn into this area, okay? What do they look like, right? Let's think about the first one. 0 to a of the same function, okay? What does it look like? There's the same function, and there's the origin in there. So I'm only considering this part. That's 0 to a, okay? What's this other part look like? This is a different function, isn't it? How's it different? It's been flipped horizontally, hasn't it, right? So I want to add together this function, but again I'm going the same boundaries, 0 to a, right? 0 to a. Can you see what happened? Can you see what, whoa, can you see what this transformation means, right? You can consider this whole part, or you can break it into two pieces down the middle. Just consider this part as usual, that's exactly the same, but then think about this part and just turn it backwards, and you'll get the same area. These two combine and you're fine, okay? So being that we can see it, how do you prove it algebraically? Would anyone like to suggest anything? What could we do apart from thinking that it works? I could do a substitution, couldn't I? I want some of this, but I think you can remember it, so I'm going to rub it off. What would be a good thing to substitute in? I'll introduce something. Let u, what should I let it equal to? Remember, this is what I'm working with here, right? So you've got x's here, but you've got negative x there. So that makes it a good candidate, right? So let that equal that. Now, when you do any substitution, right, you can't just substitute the variable. What other pieces do you need when you've got integration? What else do we have to do? You'll need the derivative, won't you? You'll need the derivative because I've got to change the variable of integration if I'm going to change the variable, right? So du on dx, of course, is just -1. You can't just change those two, though. This is a definite integral. So what else must I change? I have to change the boundaries, don't I? So, okay, I've got two boundaries. I've got x equals 0 and x equals a over here, okay? What does each one equal? For you, I mean. If x equals 0, then u equals 0, no problem. And if x equals a, u equals -a. Is that all right? I kind of cheated a little bit. I said there were two boundaries. I was only looking at this integral over here, okay? I've got another one, don't I? There's another boundary I haven't accounted for. Namely, -a, this one over here, right? It would result in u being equal to a. So now I have a choice. As with all kinds of results that you need to prove, you can start from the left, right? And then work with it to get to the right, or start with the right and go to the left. Which one would you like to do? Any takers? Right or left? Hands up for left. Anyone? Hands up for the left? Yeah, one for the left. Okay, that's fine. Hands up. Or two for the left. 2.5 for the left. Hands up for right. More people for right. Why? Because blah, 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 blah. Why? No, really. Most of you did say right. Why? You think it's easier to simplify? Go from something which has more terms to something which has less? That's probably true. You will see in a second. We can do it from either side, and it really is fine. And you need to get used to doing it from, taking something which is simple and integral and breaking it apart. That's something which is crucial to understanding this. But fine, we'll go democratically. Let's do it from the right-hand side. Okay. So let's try this. Whoops. Okay, that's what I started with. What's your first suggestion? What should I do with this to start working with it? I should split it, shouldn't I? Because this substitution u equals -x, right? It's only really going to help you work with this guy, right? If you don't want it clouded with this. And this part here already looks very much like this, right? So you don't want to muck around with it. Let's just leave him be over on this side. F of x with respect to x, and then you've got this guy. Also from 0 to a. Okay. So now at this point, you've got this ready to do the substitution. Let's do it all in one hit. Okay. This guy is still out the front, and he always will be until we combine them at the end. 0 and a are going to turn into 0 and -a, right? Is that right? Yep. Okay. What am I going to have in here? I replaced -x with a u. I'm going to replace this dx with, what does that go with? A negative du, right? So there's my -1 du. So far, so good. Okay. There's a couple of things to notice here, though. Both of the things that I drew your attention to before. Let me put this guy out the front first. I should do this in 2 steps. Firstly, this negative. We can get rid of this negative. how shall I get rid of him? It's a definite integral, right? I will get rid of this negative by turning the boundaries backwards, right? And that kind of makes sense. This is going from 0 to negative a. That's right to left, which is not the normal way we think, right? So I'm going to resolve that negative by saying this is now from negative a to 0. Is that okay? Got rid of that. But now we see, this x and this u, they're going to disappear in a minute, right? Once I actually evaluate this thing. So it doesn't matter what letters they are. I can choose any variable I like. I'll just put, instead of this u, I'll put x back in. Please notice, it's not that u equals x. It doesn't, right? What it means is that at this point, it doesn't matter what the variable is. It could be u or x or t or theta or anything I like, anything I haven't even introduced, because the same process is going to govern it and the same variable is going to disappear when I put the boundaries in. Okay, now you can see it, can't you, right? You've got the same function being integrated, right? You've got these two sets of boundaries, but they interlock at 0. And that's why you get to the left-hand side. I suppose I'll run out of space, but you can see what's going on. Kind of neat, okay? So what were the steps? What did I go through? I did this, which was kind of unnecessary, but just so I could see what was going on and know what I was doing, right? That's always nice. When you visualize it, then you turn to the algebra, okay? There's always going to be some kind of substitution involved. So just like a normal substitution, you work out how to change it. You choose a suitable substitution, you work out how to change the variable, and then you take care of the boundaries. The rest of it just plays out after you sub everything in.